Welcome to this video course on pattern recognition. Today's lecture will be a general introduction to pattern recognition. These are the reference books for the course. The first two books, Hart and Stock and Bishop's 2006 book, are very good self-contained graduate level textbooks on pattern recognition. The older book of Bishop is also a good book, especially for neural networks. I have also included a very old reference of Doda and Hart's 73 book, which actually defined the field and hence historically a very good book on pattern recognition. Even today it is worth looking at. So, now let us start pattern recognition. Pattern recognition is what everybody understands of it, is recognizing patterns. It is it's something that all of us do almost effortlessly. All human beings are capable of categorizing sensory input. So, we can think of a pattern recognition system as something that takes a pattern as an input and output is a class label. You want to categorize things. Some standard pattern recognition tasks that all of us do I have listed here. Human babies when they are quite young can start reading facial expressions of mothers. It is a very complicated pattern recognition task. You need to know whether you are good or bad, whether somebody is smiling or angry. Another thing that all of us effortlessly do is speech. We are just born with the ability to learn to recognize speech. The next three things are what can be taught to us. We do not effortlessly learn them, each with a little more difficulty. Reading is not like speaking. We have to be taught alphabets, not the other two are professional tasks, fingerprint recognition, medical diagnosis. These are things that we, in each of these cases, we look at a pattern and diagnose it or categorize it into a category. I have also put the last one. One does not know whether this is really true or not, but wine tasting is a highly prized pattern recognition ability that some humans can train themselves to. Now, this course is about machine recognition of patterns. How do we program computers or computer systems to do pattern recognition? The standard procedure followed for machine recognition of patterns is this block diagram. You take a pattern input and then it goes through what is called a feature extractor. The feature extractor makes some measurements on the input pattern. So, the input pattern is converted to now a vector of measurements, which will denote by x, which is called the feature vector. For this course, most of the measurements yield real values. So, x will be a vector in the n dimensional Euclidean space, x belongs to Rn. Then the classifier block looks at such vectors and maps them to a class label. So, a classifier is simply a function that maps each point in Rn to one of finitely many values. In a general system, features are of course very much problem specific. We will look at a few examples. Here are a few examples of pattern recognition tasks. The simplest one is character recognition. All of you would have seen OCRs. Almost every scanner today comes with an OCR system. An OCR has to take the image of a page, separate out lines, separate out words, separate out characters and recognize each of the characters. So, let us just look at how do I do character recognition. So, the pattern is an image. Somehow isolated the image of the character and the class is the identity of the character. So, if I am doing printed English recognition, then I have got 26 classes or 26 plus 26 classes if we count the capital and small letters. So, given the image of a character, output is a identity of the character. There are many features people use. You can actually use a binary image itself as a feature vector. If you resize character say to 32 by 32, we can use a 1000 bit vector as a feature vector. Other things that are often used in this task are row sums and column sums, projections of the image along various directions, or you expand image in some basis functions. Those are the kind of features that one uses for character recognition. Another example, speech recognition. Here the input is a 1D signal, one dimensional signal of speech. Output of a microphone may be the continuous signal, but if you want to do it in a computer, it is always the sample version. And the identity is the class identity is the identity of the speech unit. say for example, I want a voice activated phone. So, I'll just speak into the phone 1, 2, 5, 6, 7 and it should recognize that the first bit is 1, first chunk of speech is 1, second chunk of speech is 5 and so on. The features chosen here are obviously much different from the character recognition problem. You have to somehow get the spectral components. So, the various kinds of features people use, you take the signal and do a linear prediction coding so called, if you do not know what it is, it does not matter, or I take the speech signal, take its spectrum and look at magnitudes of various frequency components. There is a special kind of spectrum that speech people calculate called cepstrum. So, many such features are used. There is another interesting thing about this pattern recognition task. Suppose all of us know that the frequency component plays a major role of which speech unit it is, but speech signal is not stationary. So, what is normally done is you take a chunk of speech, cut it into small pieces, maybe each of about 20 milliseconds duration, and then on each such piece you do a feature extraction. So, that within that duration the speech signal is stationary and hence we can find the spectrum. Given that, what it means is sometimes a pattern can become not one feature vector, but a sequence of feature vectors. So, given a sequence of feature vectors, we have to categorize into a class. Another example, nowadays there are what are called biomouses, where after typing in your login ID, instead of typing your password for authentication, you may just click on a mouse which has a fingerprint sensor on it. So, the computer will match your fingerprint and then decide whether you are authorized to you are the same user or not. So, here the pattern is an image, that of the fingerprint, plus an identity claim, my login ID, and the output is binary here, yes or no, the 2 class problem. There are various kinds of features extracted from the image. These features are obviously different from what you extract from the image of a character for character recognition. They are what are called minutiae, and the features extracted are the position and orientation fields of minutiae and so on. Another example, video surveillance system, these days we see them in many airports. So, what is the pattern here? It is a video sequence. A video camera is scanning a scene, and what is the system supposed to do? Alert you on some security breach. So, we can have different classes based on level of alertness. Right. Normally, in simplest of such systems, you are looking for suspicious motion. So, you want to process the image, follow motion trajectories, try and characterize object motion, and then use those features to decide whether or not there is some suspicious motion. So, here the pattern could be a video sequence. We have seen different example. The one example where pattern is an image, another example pattern is a 1D signal, the speech. Here pattern is a sequence of frames, actually a video sequence, and accordingly the features measured are also different. Right. Many such examples we can give. Many credit card companies these days use programs to do credit screening. So, here the input pattern is a detailed application, then the features to measure are income, job history, level of credit, your old credit history, and once again is a binary classification whether you are credit worthy or not credit worthy. Same thing about imported detection. Some credit card companies try to guess whether a card is being used illegally. So, once again it depends on features such as amount of money withdrawn, location of transactions, times between transactions. Given the previous history of the card holder, anything that looks anomalous can be flagged, and once again is a binary classification task. Other thing that all of us are familiar with is searching on the Google. So, this can also be thought of as a pattern recognition task, so slightly different. So, you can think of the pattern as a document and a query. For each given document and query, you want to say whether it is relevant or not, because in general we have many documents and a query and we want to rank, but you can still think of it as a pattern recognition task, where the input pattern is a document and a query and the output is relevant or not relevant. And the standard features used are word occurrence counts, context, word context, that is bigrams of couple of phrases, how often they occur in a document, and so on and so forth. Okay. So, what we have seen is a whole set of examples of pattern recognition. So, one thing that comes out clear from these examples is that the features depend on the problem. So, depending on the problem, whether if it is speech, you measure spectral components, if it is a video surveillance problem, you try to characterize motion trajectories and so on. So, the features that you want to measure obviously depend on the problem. The only generic thing that we can say is sometimes having measured some features, we can transform them to so that they become more relevant for our classification task. There are techniques such as PCA, which stands for Principal Component Analysis, which we will see later on in the course. So, there are some general techniques available to extract more relevant features, but in general in a pattern recognition task, feature extraction is very much problem dependent, and it often depends on what all you can measure, what all you can think of measuring. After feature extraction, every pattern is a vector, and classifier is a function that maps such vectors to class labels. So, what we consider are there are many general techniques for classifier design, where the classifier is viewed as mapping vectors into class labels, and that is what the gist of this course is about. We will consider various methods of designing classifiers, where from now on for us a pattern is synonymous with a feature vector. Right? Okay. So, here is the notation. Let script x denote the feature space, it is so called feature space, which is the space of all possible feature vectors that we can ever encounter, that the classifier will ever encounter. Then a classifier is a function, sometimes also called a decision rule, which maps the feature space to the set 1 to m if we think there are m classes. So, what characterizes pattern recognition is that the output is finitely many, it is a categorization task. Given some continuous input, I am categorizing the input into finitely many. I look at when I am teaching my son the concept of a dog, I show him so many images, so many real dogs which are also images for him, and he has to somehow see what is common to all of them, so that he can characterize a new image now as a dog or not a dog. So, a classifier maps this continuous feature space into one of finitely many class labels. For us, often x is n-dimensional Euclidean space if we think there are n measurements. It is convenient often to consider the case m is equal to 2, which is called the 2 class problem. When we consider 2 class problem, we take the labels to be either 0, 1 or minus 1 plus 1. If you do that, any binary valued function on the feature space is a classifier, right? Is by definition a classifier, but of course, not all classifiers are equal. For a given problem, we want that function which does well. So, first question is what h to choose. Then we say we want correct or optimal classifier. Then the next question is how do I define what is correct, what is optimal, what kinds of criteria can be used for optimality. Given a particular criterion, how does one design a classifier? If I design a classifier, how do I judge its performance, how do I test its performance, and can I theoretically give any performance guarantees because of the particular method I follow for design. These are all the issues that we would be dealing with in this course. For most of the course, whenever we consider technique, we will always first consider the 2 class problem. One can handle the more m class problem if we know how to handle the 2 class problem. For example, at this stage I can tell you one simple method. You can design if we can design m 2 class classifiers, then we can solve an m class problem. For example, I want to solve the 26 class problem of recognizing English alphabet. I can design a classifier that says A or not A, another classifier that says B or not B, another classifier that says C or not C. Then I give the pattern to all of them. When only one of them says yes, the other says no, then I know which character it is. Such a method of designing m class classifiers using a number of 2 class classifiers is called one versus rest approach, and this is very often used and in many cases successful. Of course, there is always a problem with this. Suppose my A versus not A classifier also says yes, my B versus not B classifier also says yes, then I do not know whether to call it A or B. So, the one versus rest classifiers sometimes gives you ambiguous decisions, one needs to know how to handle it, but this is at least one in principle method of learning m class classifiers from 2 class ones. There are other possibilities, what I call tree structure classifiers. In any case, the 2 class problem is the most basic problem, that is what we will always first start with, and we will of course also look at the m class classifiers. So, let us consider a simple 2 class problem. I call the problem spot the right candidate. Many of you would have gone for some interview or the other, and at the simplest level, the interview panel has to make the decision whether a candidate is good or not based on at least two features. One feature sums up the academic record of the student. Let us say for a student coming for a first job, marks obtained in his degree, and the second feature is marks in an interview. So, the candidate is interviewed and the interview panel also gives some marks. Given these two numbers, one has to make a decision whether the candidate is good or not good. So, for example, I can have a classifier which says for some AX1 plus BX2 greater than C means the candidate is good. So, I am saying some linear combination of the marks is greater than some threshold, then it is good. So, the question is what weightage I want to give to different marks. Of course, this is not the only classifier. For example, in principle, based on the values of A, B and C, is possible that even if x1 is 0, if x2 is sufficiently high, a candidate may still be good. Whether we want that or not is up to us. If we do not want us, maybe then we can take a hyperbolic classifier, which says if product of x1, x2 is greater than something, then the candidate is good. So, there even in the simple problem, design of classifier involves what structure of classifier we want to choose. So, we choose a specific form for the classifier, and also if we choose a specific form, we have to choose what parameters to use, what values for A, B and C we use. Right? That is what constitutes the design for the classifier. Now, how do we design? Need to decide how feature vector values determine the class. In our simple problem, we need to know how different marks reflect goodness of a candidate. At 60% in your interview and 80% in your university marks, is it better than if 70% in interview and 70% in university marks? I do not know. Right? So, those are the kind of issues that one has to determine. The problem is, in most situations where pattern recognition techniques are used, it is not possible to derive this from any theory of the situation. For example, in this case, there is no theory of how marks are given. So, that using the physics of the problem, so to say, I can derive what linear combination is the best linear combination. Why is that so? This is because there are a lot of variability in patterns of a single class. Right? In my simple problem, good candidates sometimes may do well in academic record, may not do well. Sometimes some people are good at written exams, some people are good at oral exams. So, there is a lot of variability in the patterns of a single class. If you think of character recognition and think of all the ways different people write their A's and B's, or all the different calligraphic A's and B's that you can recognize. There is a lot of variability in the shape of the characters, and still all of us know what is a what is a B. So, there is a lot of variability in patterns, which of course translate to variability in feature vector values. So, if I measure for any given set of features that I choose, if I measure the feature vector values for many different A's and B's, for example, I will get different numbers. So, there will be a lot of variability in feature vector values of patterns belonging to the same class. Also, patterns belonging to different class can have arbitrarily close feature vector values, because my feature measurements are arbitrary. It is not determined based on a measurement that is known to be discriminatory. I just measure what I can. For example, in the character images, we just measure maybe row sums, column sums, some projections, some movements. So, none of them have anything to do with A's and B's. So, feature vectors of patterns from different classes can be arbitrarily close, and of course, there is always noise in measurement. So, given this much variability, it is not possible to design the classifier from any first principles. Then what do we have? So, the only information available for designing a classifier is what is called a training set of examples. I am given a training set xi, yi, I going from 1 to L, where each xi is an example feature vector, and I am told what is the class of that yi is. You can think of this as the way we learnt our first alphabet. The teacher writes on the board or maybe shows a card of shape of A and says this is J, and she writes a B and says this is B. Okay. So, she writes J many times, B many times, and then we somehow learn to recognize those shapes. Okay. So, you are given a training set of examples, and just using that we have to design a classifier. How do I generate the training set? Of course, training, because I do not have any classifier. If I have a God given classifier which can classify feature vectors correctly, then I do not need to design any other feature pattern classifier. So, even if I measure features on some random patterns, I do not know how to get y. So, the way I generate training set is take representative patterns from the category. So, for example, if I want training set for character recognition, I go to 20 people, give them rule sheets and ask them to write many A's and many B's. Now, then I take images of each of them and do my feature measurement. So, I get feature vectors and the class of a feature vector is known because that has come from some shape which the person who wrote the shape said is A. So, what you say is A, what you say B is B, that is how I know the class labels. So, in general, I generate the training set by taking representative samples from the respective categories. Now, we have to learn the appropriate classifier, right, by using the training set. So, coming back to our simple problem, spot the right candidate. Let us say we chose a linear combination classifier. We chose the structure of the classifier to be AX1 plus BX2 is greater than C. We have chosen a specific form for the classifier. So, what is the information available for us? The experience of the people making the decision. They have seen history of candidates. So, for example, the information can be represented like, on the x1, x2 space, which is my feature space. I can put these points, each person will become a point there and I know who performed well afterwards, who performed poorly afterwards. And so, for example, those big dots, let us say, are good candidates, small dots are bad candidates. So, given this experience, I want to know which line is the best line to separate them, or put one line that separates. So, in general, that is the way I will learn a classifier from a training set. So, here is another example. Suppose I want to teach somebody the concept of medium build, right. Of course, we know that medium build means a range in height and weight, but the person learning it does not have that concept. So, we just show him a lot of examples of people who are medium build or not medium build. So, for example, here once again there are two sizes of dots. We want to separate one size from the other, but what separates now is not a line, but a rectangular enclosing box. So, the classifier is non-linear here. Okay. So, the boundary between classes can be captured by a line or a hyperplane in general, or may not be captured by a line, but may need more complicated surface like a rectangle here. So, you can think of designing a classifier as a problem of learning from examples. Okay. Sometimes it is also called learning with a teacher. So, you can think of it like this: there is a teacher who is trying to teach, much like the way we learnt our alphabet. So, the teacher sets out a problem, namely shows me a card on which something is written. Then the learner gives some answer, I shout out A, then I get a feedback whether what I said is right or no, you should have said B or you should have said C. So, this setting out a problem and feedback is what the training examples are all about. Now, in general, of course, pattern recognition is only one example of learning, one instance of learning from examples. In general, this kind of thing can be used in many different situations. Learning to ride a bicycle, is also something that we do. Now, all these can be captured into this block diagram by saying that the nature of the teacher's feedback can be different. So, once again, in the context of pattern recognition, so what we are saying is you set a feature vector at the problem, the classifier outputs a class, then I got a feedback from the teacher which tells me the right class, that is the xi, yi in the training set. Now, this kind of learning is called supervised learning. Here the teacher gives the true class label for each feature vector. So, the teacher is very nice, very informative, like my teacher in teaching me the characters tells me what I should have said for that character. There are other kinds of learning situations that are also important, though not considered in this course. It is called reinforcement learning, where the teacher can only tell you whether doing poorly or well. So, that is called reinforcement learning. For example, learning to ride a bicycle is not like learning an alphabet. There also I need some instruction, but that is mostly done by doing. The feedback I get is how long I have been able to balance, how soon I fell, when I fell, and somehow using this we learn to learn the right coordination. Right? So, in reinforcement learning, the teacher just provides a noisy assessment of performance, and there is also unsupervised learning problems where there is no teacher at all. Just by looking at all the examples and the structure inherent to them, I want to somehow categorize. Sometimes this is called clustering problem. We will not consider either reinforcement learning or unsupervised learning in this course. Okay. So, we will essentially be considering supervised learning, where the teacher gives me the true class label. So, I have my xi, yi, but when I say true class label, there is inevitable noise in any training set. So, we will always budget in our design for some of the labels in the training patterns given by teacher may not be correct, right. We consider it still a supervised learning with noise, and we like classifiers that can withstand such noise, that are robust to such noise, okay. And almost all classifier learning algorithms do supervised learning, okay. So, we will be considering various supervised learning algorithms for learning classifiers, okay. Before we complete our generic introduction, there is another very close related problem, and this will also form part of the course, which is called function learning. It is closely related to pattern recognition. Here also you have training examples xi, yi. The only difference is yi, instead of taking finitely many values, in the classifier case, that it takes finitely many values and the values are the class label. Here yi takes continuous values. So, here what I call the prediction variable y is continuous rather than taking finitely many values. However, I still need to know, given these examples, if you give me a new x, what will be the corresponding y. So, similar learning techniques are needed to infer the underlying function relationship between x and y, right. So, this is called function learning. Just like we saw examples of pattern recognition, we can also look at examples of function learning, right. So, a simplest example of functional learning is time series prediction. Given a series of numbers x1, x2 up to xn or xn minus 1, I want to predict the next number xn, right. What could be? So, I want to find a best function which predicts xn. So, because predicts, I put a hat on top of xn, I will call it xn hat, is some function of xn minus 1, xn minus 2 up to xn minus p. So, I want to predict the next number as a function of the previous numbers. For example, I may want to predict stock prices. What will be tomorrow's stock price based on the stock prices over the past few days. I may want to predict exchange rates. If I am a banker, I may make a lot of profit by buying and selling foreign exchange. So, I want to predict exchange rate fluctuations. Many compression, speech signal compression problems, which some of you might have studied, uses linear prediction models for speech. So, given some speech, I may not want to transmit the whole of it, if I can predict some part of the speech based on the previous speech. So, I can once again learn a function to predict. There are quite a few compression algorithms that use such prediction models. More general function learning problems can include prediction that don't use only the previous values, but use extra variables also. So, I may want to predict rainfall this year based on rainfall's previous year's data or previous few years data, and also some measurements I made this year. So, in general, any system identification problem is also a function learning problem. We will consider function learning problems also in this course, which are often called the regression problems, and classification and regression are often viewed together because similar kind of learning techniques are needed for each other. Okay. So, here is a simple example of a function learning task, which many of you who studied communications may know. So, there is a transmitter like in any communication system, which sends some signal through a channel. Because the channel distorts the signal, if the transmitter has put out xk, the channel puts out zk. Now, at the receiver end, I want to design a black box, which I call a filter, which takes in input at zk and gives me some yk, and I want to do the filter design in such a way that yk is close to xk. For example, I may decide to get my yk as some linear combination of the past values of z. Very often that kind of filters work in this problem. So, what I am asking is, what AIs will give me the best chance of yk being close to xk. So, if I know some xk's that is transmitted, and then I can measure the channel input zk. So, then I pass it through this filter. So, filter gives me some yk. I can ask, is yk close to xk or not, right. So, my training examples here would be the zk at the input, that's what takes the role of xi, and yk at the input, that takes the role of y. Okay. So, I can get xk zk as the input, xk the true output I should get, and zk the input. So, I should have written it maybe as zk xk, and this learning has to be done at the receiver end. So, the receiver has to know what was sent, but how does it know? If it already knows, it does not need the filter. Often what happens is that we have some communication protocols whereby we know when a new session starts, the first few bits enter previously agreed bits. So, I use that information, I measure ZK for those time instants, right, and then I adopt my filter coefficient CAI, so that the filter output is as close to XK as possible. Right. This is a standard functional learning task, often called the equalizer. So, learning from examples, going back, is basic to both classification and regression. In both cases, we have a training set x1, y1, xl, yl. Right. There are some L examples. So, x's are the feature vectors are input and y's are the class labels are the output, and we essentially want to fit a function y is equal to fx. The function is binary valued or finitely many valued if it is a classifier. It could be continuous valued if it is a functional learning problem. In both cases, given some training set, we want to fit a best function. Now, this is not an unfamiliar problem for many of us. Right? If x is an OR, this is the familiar curve fitting problem that all of us did in class 12. Right? Given some numbers x1, y1, x2, y2, we want to fit a curve. We can fit a straight line, we can fit a quadratic. Right? So, what do? We do least squares curve fitting. So, given x1, y1, x2, y2, xl, yl, we say that y is equal to mx plus c. So, I will calculate mxi plus c as what should have been and see the error from y, and based on that error, I try to find the best m and c for the line. Right? This is the curve fitting problem. But one point that I want to emphasize here is that nobody tells me whether f should be linear, whether f should be quadratic or whatever. So, the choice of the form for f, which is called model choice, is very important from a statistics point of view. Just to understand what it means, let us suppose x is a single real number, x belongs to R, and let us say we chose f to be a polynomial. Then, if I choose a higher degree polynomial, I can get better fit. I can, and the training set, I can fit better. For example, if I have 20 points, xi, yi, and if I choose a 28 degree polynomial, then I can get perfect fit. I can get 0 error on the xi, yi, right. Just like if I have 2 points, I can get 0 error with a straight line. But that is not what the fit we want. That will be fitting all the noise. Right. So, the question of what f to use is important, and that is not determined by how well I do on the training data. I can always find f that do perfect on the training data, but they are not useful. So, what we want in learning from examples is generalization, right. For example, when we are learning our characters from our teacher, we do not want photographic memory of what teacher wrote on the board. Somehow looking at many A's, we need to abstract out the concept of A, so that now we can recognize any kind of A anybody writes. Right. So, to obtain a classifier or a regression function, we use the training set, but we know the class labels of the patterns in the training set. Hence, really errors on the training set is not a good indicator, not necessarily a good indicator of how good our classifier eventually is. For example, any classifier that amounts to only storing the training set is useless. We are interested in the generalization abilities of a classifier. We ultimately need to be able to give some guarantees on how our classifier, which is designed on some training set, will do on new unseen patterns. The training set is used to design it, but just reducing the error to 0 on the training set is not necessarily good always. Of course, we will see when it is good, when it is not good, and so on. This is part of what is called statistical learning theory. We will come to that later. But at this point of time, we want to remember that what we are interested in is whether or not the classifier that we learn from our training set generalizes well. So, the classifier should perform well in spite of inherent variability patterns and noise in feature vector under the class labels, and ultimately it should generalize well. Now, statistical pattern recognition, that is what we consider in this course, is an approach to classifier design or classifier learning, where variabilities in the patterns, variabilities in the feature vectors, which are what are the real difficulties in designing classifier, these variabilities are captured through probabilistic models. That is, we can think of a feature vector coming from one class as a random variable, which can take different values with different probability. So, it is saying that the reason why measurements made on A's written by different people will give it different numbers is that the feature vector of class A is actually a random variable, and hence it has a density function, associated density function, which tells me what all values it takes with what probability. Statistical pattern recognition is not the only approach. There are other things, syntactic pattern recognition and so on. We will not be considering any of them. Okay. In this course, we will be considering mainly statistical pattern recognition. In statistical pattern recognition, the feature space is X. We consider two class problem for our initial notation. A given feature vector can come from different classes with different probabilities. So, let us denote by F subscript I the probability density function of feature vectors that come from class I. So, F0 for class 0, F1 for class 1. Fi are called class conditional densities. So, if I think x1, x2, xn are the components of an n-dimensional feature vector, we think of them as random variables, and then the conditional joint density of x1 to xn conditioned on x coming from class 0 or class I is Fi. So, F0 is the conditional joint density of x1 to xn conditioned on the feature vector x coming from class 0. Okay. So, class conditional densities model the variability in the feature values. For example, I can have two class problem where the two classes can be uniformly distributed in the two regions. By that what I mean is all feature vectors coming from class 1 are uniformly distributed in the region written class 1, and similarly for class 2. This of course, a very nice pattern recognition problem, such things do not come often, because here the two classes are separable. A particular feature vector value comes from can come only from one class. So, I just have to know the extent of values of the two classes to decide the classification. Right. Even in separable classes, ultimately, because the feature vectors are not two dimensional, hence I can't create such pictures all the time. Even when they are separable, I need to know what kind of surface will separate them. For us, something that is very important is what is called linear separability. For example, the left panel, the two classes are separable by a line, whereas on the right panel, the two classes are not separable by a line. I can't draw a line keeping all the class 1 patterns on one side and class 2 patterns on the other side. Right. So, even when they are separable, classes may be linearly separable, may not be linearly separable. Of course, in general, classes will not be separable. So, the region over which class 1 feature vectors have non-zero probability and the region over which class 2 feature vectors have non-zero probability can overlap, which we say the class conditional densities overlap. Right. Then of course, I cannot get a perfect classifier, a classifier that makes 0 errors, but I may still want to have a classifier that is somehow good. Right. So, the statistical viewpoint, thinking that feature vectors are random variables and have their density functions, gives us one way of looking for what can be optimal classifier. It at least tells us one kind of optimality criteria we can ask for. For example, we can say we want a classifier that has least probability of misclassifying a random pattern. Right. Let us for this class quickly derive what we mean by least probability of misclassification by putting some notation now. Let us say Qi of x is the probability that class is I for a given vector x, that is given the random variable x, what the probability that it comes from class I. So, Qix obviously the function of x is conditioned on x. These are called posterior probabilities or posterior probability function for class I. Now, consider a classifier. A classifier is a function that maps x to 0, 1, because we are considering a two class problem. Right. So, a classifier is simply defined as for which all x it is 0, which all x it is 1. So, I define a classifier h of x which takes value 0 if q0x is greater than q1, takes value 1 otherwise. That is, when I given an x, I calculate the numbers q0x and q1x. If q0x turns out to be higher than q1x, then I will put it in class 0, otherwise put it in class 1. Because q0 is the probability that it comes from class 0, q0 is greater than q1x would intuitively imply that the feature vector x is more likely to come from class 0 rather than from class 1. So, intuitively we should think that such a classifier will minimize probability of classification, probability of error in classification. So, we will actually prove it later, but let us just look at how can we formalize at least the concept of probability of error. So, let us say x, which is for us n-dimensional real Euclidean space, is the feature space. and y is equal to the set containing 0 and 1 is the set of class labels. So, we are considering a 2 class problem. Right. Whenever we are considering designing classifiers, we should ask what all classifiers we design, say linear classifiers, quadratic classifiers. So, we may have some set of functions which is the set of classifiers of interest to us. Any classifier is a function that with domain script x and range y, for each feature vector I assign a class label. Every such function is a classifier. There are some set of functions that I choose which are the classifiers of interest to me. Now, out of this bag of classifiers, I want to know which is the best classifier. So, which means for every such classifier, I want to assign a figure of merit. Okay. To assign a figure of merit, we would need how well the classifier does on various feature vectors. So, as a notation for a given feature vector x, let us say y of x denotes the class label of x. Because the same x can come from different classes with different probabilities, yx is not a deterministic function, it is a random function. Given an x, y of x can be 0 with some probability, 1 with some other probability. So, y of x is a random variable which is a function of the random variable x, right. So, with that notation, let us go and define some figure of merit, so that for each classifier we can say how good or how bad it is. So, one figure of merit could be for each classifier h, I assign a number f of h, which is capital F of h, which is probability that hx is not equal to yx. H of x is what the classifier would say on x. Y of x, so to say, is what the nature would say on x, right. That is the unknown true class for the pattern x. These probabilities are with respect to the underlying probability distributions of x. So, probability hx is not equal to yx is the probability that on a random x, my classifier h will make an error. So, fh is the probability of misclassification by the classifier h. So, I am asking among all classifiers, which classifier has the least value of f of h. Right? So, optimal classifier can now be defined as one that has the lowest value of f. Okay. Now, given a particular classifier h, we can't calculate f of h unless we know all the underlying probability distributions, right. I need to know the distribution of x and I need to know what kind of function y is of x, and then I can calculate that probability. Even if I can, I do not know how to minimize this f. Okay. H's are various functions, how to minimize it over various functions. So, it is not a straightforward optimization problem, but let that be. We will look at solution techniques later on. Right now, I just want to formulate what is an optimal classifier. Okay. There is one more thing that it doesn't take care of here. I am only looking at errors. So, I am asking what the probability it makes an error. I am not saying whether it is classifying class 0 pattern as class 1 or class 1 pattern as class 0 pattern. So, all kinds of errors are same. In general, they are not. Okay. Sometimes we will see examples later on, I will come to that later on, but sometimes classifying a class 0 pattern as class 1 pattern may incur more cost than classifying a class 1 pattern as class 0 pattern. In that case, just simply making probability of making an error small may not be what you want, but does not matter. Let us stick with this. We just want to minimize probability of error. Now, I will give you a classifier that minimizes probability of error, which is called Bayes classifier. Before that, let us just recall some notation. Fi of x is the probability density function of feature vectors of class I. Pi, which is the probability that y of x is equal to I will call prior probabilities. That is, if I do not know any x, I am just asking what is the chance that I get a class I pattern. So, these are called prior because I am just asking what is the chance I get class 1 patterns or what is the chance I get class 0 patterns. We already defined posterior probabilities, and by Bayes theorem, I assume all of you know Bayes theorem, Qix, that is probability yx is equal to I given x, I can invert it, that is Fix, which is x density of x condition on yx is equal to I into probability yx is equal to I. So, Qix is Fix Pi by some normalizing constant in the Bayes theorem. So, Bayes theorem tells me that if I know class conditional densities and prior probabilities, I can calculate the posterior probabilities up to a normalizing constant. So, now consider this classifier. Hx is equal to 0 if q0x by q1x is greater than 1. This is the same thing what we consider like q0x greater than q1. Okay. is 1 otherwise. This classifier is called the base classifier. Okay, it's called base classifier because I actually calculate Q0 and Q1 using F0, P0 and F1, P1 and based on base theorem. From what I spoke to you earlier intuitively, Q0 is greater than Q1 means there is more chance that X is coming from class 0 than class 1, and hence we would expect this to be optimal, and it is in fact optimal. We will prove that base classifier is optimal in the sense that no other classifier can have lower probability of error than base classifier. I emphasize once again that Q0 and Q1 can be calculated if I know P0 F0. In particular, Q0 x greater than Q1 x is same as P0 F0 x greater than P1 F1 x. So, I will always implement base classifier by knowing class conditional densities and prior probabilities. Of course, at this point of time I do not know where I am getting them from, but we will come to that later. So, this is an example classifier. For the first class, we will at least look at one example classifier. This is a very good classifier, it is not any trivial classifier. It actually minimizes probability of error. Okay. The only thing we do not know, so we have designed a classifier that minimizes probability of error. The only thing we do not know is how actually we will calculate the classification decision. Given an x, to calculate h of x, I need to know Q0 and Q1 to the functions. To know the functions Q0 and Q1, I need to know P0, P1 and the class conditional densities F0 and F1. So, if somebody gives me P0, P1, the class conditional densities F0 and F1, then I can implement base classifier. But for the moment, not worrying about that, in the next class, we will certainly prove the optimality of the base classifier. Okay. So, let us sum up what we said in the introduction talk. The machine recognition patterns, the pattern recognition is a two-step process. It is consisting of feature measurements and classification. The first block, given any pattern which could be an image, which could be a one-dimensional signal, which could be combination of these, it makes some measurements, converts into a vector of measurements, that is called the feature vector. And for us, feature vector is a n-dimensional real vector, that is it resides in the n-dimensional real Euclidean space, and the classifier, the classification block takes such feature vectors and assigns class labels. A classifier maps feature vectors to class labels. So, it is a function from the feature space to the set of all class labels. The main difficulty in designing classifiers is due to the large variability in feature vector values. So, when we take patterns belonging to the same class and make feature measurements, there is a lot of variability in these values. Patterns coming from the same class can give you widely differing values, pattern coming from different classes can give you very close values. So, that is the difficulty that we have to handle, and the only information we have for designing the classifier is a training set of examples. Right? Training set of examples consists of xi, yi, where xi is a feature vector and yi is the true class for the feature vector xi. I generate the training set by actually sampling from the respective distributions. We also saw that functional learning is a closely related problem, where the output, instead of being a category, instead of being finitely valued, is actually a continuous valued number. Okay. In both cases, we need to learn from examples. The statistical view is that we model the variation in feature vectors of a given class through probability models. So, we will say that all feature vectors coming from class 0 take different values at different probabilities as given by a density function or mass function f0x. Those are called the class conditional densities. So, the statistical view models variations in feature vector values through probability models. Then, for example, in this class what we saw is such a viewpoint gives us at least one advantage. We can define what is a optimal classifier. For example, we can ask, find a classifier that has least probability of error. The characterization least probability of error makes sense because we have a statistical viewpoint and we are modeling feature vectors as random variables with given class conditional densities. So, for that criteria of optimality, having least value of probability of error being your criteria of optimality. Bayes classifier is the optimal one. So, if we know the class conditional densities and prior probabilities and hence can calculate posterior probabilities, then Bayes classifier can be implemented, and as we shall show next class, Bayes classifier is optimal in the sense no other classifier can have lower probability of error than Bayes classifier. Because in the first class, I will end the class with a rough organization of the course. So, in the next one or two talks, we look at a general overview of classifier learning strategies. So, we will look more closely at Bayes classifier, and also we will look at many other kinds of classifiers called nearest neighbor classifier and so on. Okay. And then I will give you a rough overview of various classifier design methodologies and how they fit in. Then we will go into each of them in depth. We will first look at Bayes classifier that minimizes what I call risk, which is generalization of probability of error. Then we will look at some variations on the Bayes classifier. Then we will look at how one implements Bayes classifier, how does one get class conditional densities and prior probabilities so that Bayes classifier can be implemented. Okay. Then we will look at, okay, if I can't get class conditional densities, what else can I do? We will look at techniques what I call linear discriminant functions. We look at special algorithms for learning linear discriminant functions. We will also look at function learning using linear models, what I call linear least squares regression. So, once having seen some examples of how to learn classifiers, we will take a step back and look at the theory of learning. We look, of course, we will not do at any great depth. This is a first level course on pattern recognition. So, we will look at very simple overview of what is called statistical learning theory, and one topic there was called empirical risk minimization, which is what most classifiers follow. So, we will give some statistical theory to justify the kind of classifier design strategies that we follow. Then we look at nonlinear classifiers. Till all the discriminant functions that we look at in the beginning are all linear. Then we look at learning nonlinear classifiers. We will essentially look at two kinds of methods there. One are what I call neural networks, other are called support vector machines. Support vector machines belong to a class of methods called kernel based methods. So, we will look at in detail designing nonlinear classifiers both for both using neural networks and using support vector machines. And then we will look at a little more theory of support vector machines, what I call kernel based methods. Kernel based methods today are possibly the best off the shelf strategies for designing classifiers. Then we will look at a few special topics. Two topics we will certainly look at are some feature extraction and dimensional reduction methods, what are called principal component analysis. And then we will look at another technique for classifier design, what is called boosting. All the first part or almost till the end, we will be only looking at, given the training set, how to learn one classifier. The boosting technique is not to learn one classifier, but learn many classifiers. The idea is that if we can't learn one classifier, that is very good. If I learn many independent classifiers using the same training set, can I somehow get better than a single classifier? So, if I have 10 different classifiers, each of them is asked to do the classification of the same unknown pattern, and then we take majority decision. Sometimes we may do better than using any one classifier. Right? So, such boosting methods for example, are similar to the audience poll in Kaun Banega Crorepati kind of programs, right, where each member of the audience may know the correct answer with probability only 55%, 60%. But if you ask enough of them, we would know what is the correct answer. So, ensemble classifiers is something that has become very important in the field in the last 10 years. So, that is also one topic we will consider. After that, time permitting, we will look at a few more advanced topics in classification such as Bayesian networks. Okay. So, that is the overview of the course, and thank you at the end of the first lecture.